And welcome everyone to Calculus 2, where it's an odd thing to be starting this in the middle of the semester, but we'll make do as best we can. Where we left off before spring break is we had just started at section 8.7 in our textbook, which is called Approximating Integrals. We're going to start off by just doing some review of this. What we ended up with is two methods, the Simpson's rule and trapezoidal rule for approximating integrals. That was slightly better than just using the rectangular approximation and midpoint using either an endpoint or a midpoint or some point in the middle we'd done in chapter 5. And those rules are both summarized here. You can see with the trapezoidal rule we're taking our common difference, our delta x, dividing it by 2, and then summing up the y values where every y value but the first and last are all multiplied by 2. Simpson's rule is similar, except you're taking the delta x divided by 3, still leaving the first and last y value alone, but you see here we have a repeating sequence of times 4, times 2, times 4, times 2, etc. till you get down to the end where you have, your last times 2, last times 4, and then this. For Simpson's rule, I didn't write it here, but you do need an even number of subintervals to use it, whereas for trapezoidal rule, you can have any number of subintervals you want. So we're going to practice this in this video, and that'll be it. I'm trying to keep the videos short. You may have to watch a couple of them in a day, but at least you'll have a convenient little break point. And here we go. Here's our first exercise. This is from our textbook. It's section 8.7, problem 8, from page 502, if you want to look up the reference. I did choose an even number of subintervals to use. The book uses 4 instead of 6. I thought since we had time, we might as well use the 6. So we're going to use both trapezoidal rule and Simpson's rule. Then we're going to find the integral directly and find the errors. Then we're going to express the errors as a percentage of the integral's true value. Alright, let's start off here. First thing to do is figure out what the common difference is. So let's see, our delta s in this case, oh goodness, my s's look so much like 5s. Delta s equals, let's see, 4 minus 2 over, and we want 6 steps, so 6, that is 2 over 6, or 1/3. So then our intervals for either rule are going to be, or let's actually not call them in. Let's just do our endpoints because we actually have to find all of those. All the points we're plugging in would be, well, we'll start off with 2, then 2 plus 1/3. Let's see, 2 is 6/3, so that'll be 7/3, 8/3, 9/3 is 3. I'll just keep going with this. It'll be convenient to plug into the calculator this way. 10/3, 11/3, and 12/3, or 4. That is 1, 2, 3, 4, 5, 6, 7, which would mark off 6 subintervals. Alright, doing trapezoidal rule. Well, that would be delta s over 2 times the sum of the s sub k values, the y sub k, I guess is what I will call them. So that would be 1/3 over 2 times, well, here's our function, 1 over s minus 1 squared, so it'll be, 1 over 2 minus 1 squared plus 2 times 1 over 7/3 minus 1 squared, etc. So let's get our calculator out. let's see, how do I want to do this? I think it's probably easiest if you set it up like this. 1 over x minus 1 squared. And then you just use your function. So we go into the variables menu, over to y variables, hit y1, plug in our first value, enter. Alright, now we're going to add, so plus, y variables function, y1 of, alright, our next one was what, 7/3? 7/3. Up. There we go. Up. One of 2. And what I'll do this time is y1 of 2. I'll just get that and add the answer to that. Although I also need a 2 for every other point except the first one and the last one. So let's see, I need a 7/3 in here. There we go. Alright, now we're ready to iterate, so I'll change this to 8/3, 9/3, 10/3, insert, there we go, 11/3, and for the last one we need to take off the multiplication, so go down here and change that to, get rid of the 2, change that to 12, and there we go, 4.11. Now remember, this is just the sum, all the stuff in the parentheses. I now got to divide that by 6 to do the times 1/6. So divided by 6. So that is 0.68412. That's enough accuracy for what we're going to be dealing with. Alright, then we have Simpson's rule. Although, instead of just saying Simpson's rule, I'd usually say T6 equals and S6. That actually denotes which one is which. So this would be delta S over 3. Oop, that looks like an A. Delta S over 3 times the sum of y sub k's. That's not even all that accurate, you know, because it's still, these things have multiples on them too, so we're looking at 1/3 over 3 times, we'll call it this one, y of 2 plus 4 times y of 7/3, 4 times y, plus 2 times y of 8/3, plus 4, etc. So let's go back up and start off again and change my, I might as well just start here. Y1 of 2. Just change this since I'm going to have to do it anyway. Alright, there's that. Now, because this is a more complicated iteration, I am going to add an additional term. So plus 4 plus 2 So this one should be 7/3. And this one should be 8/3. This will move us pretty quickly through our terms then. So we do that. Go up here, change this to 9 and 10. And one more. This becomes 11. And since this is the last term, I have to take off the 2. This becomes 12. And we're left with... Oh, not done yet. I almost forgot. Still got to divide by 9. Because I got to do the 1/3 divided by 3. Okay, now... we got 0.66788. So we have 2 approximations for the integral. So now, let's see what the actual integral would be. Actual integral. I think, looking at that, we just have the integral from 2 to 4 of s minus 1 to the -2 ds. So that we ought to be able to do with a pretty simple substitution, just because the derivative inside is just 1. So yeah, if we let u equal s minus 1 du is ds, this becomes, might as well convert the limits over as well. 2 minus 1 is 1. 4 minus 1 is 3. This becomes u to the -2 du. And then that becomes 1 to 3 negative u to the -1. So that's 1 to 3 -1 over u. So that is -1/3 plus 1 or 2/3. So that's the actual integral. You can tell Simpson's rule is a little bit closer than trapezoidal rule, but they're both not that far off. Find the errors. So the error in the trapezoidal rule, 2/3 minus 0.68412 and 2/3 minus 0.66788. So our error in the trapezoidal rule, I'll go ahead and do it in absolute value, is 0.01745. Our error in Simpson's rule is 0.00121. So those are our errors. Found our trapezoidal approximation, Simpson's rule approximation, found our actual integral, found our errors. Lastly, they want us to express the errors as a percentage of the true value. So, I mean, that would just be take the error, put it over the actual integral. So that will be 0.01745 divided by 2/3 and 0.00121 divided by 2/3. .01745 divided by, probably should have just done the fraction work myself. Times 3 divided by 2. Oh well. So, as a percentage, it doesn't really say where they want us to round this. I'll assume to a whole percent. Oh, 1, 2, 1. Well, let's be consistent. This one would be 0 if I rounded to a whole percent, so let's round to 1/10%. So this will be 1.7%, and then this would be 0.1. Make that point a little bit bigger. 0.1%. So those are the percentage of the integral's true value. The percentage error. That's where we're going to end this video. We'll pick up next time and look at estimating errors for these different methods. It's all very well and if you can already calculate the integral, but in a lot of cases we'll be using this when we don't know how to calculate the integral. So for those, it'll be nice to know how close we're getting with our approximation. See you then.